Hi everyone. All right, this lesson will be kind of quick today, and I know you guys have a lot of time, so I'm hoping you can use it to review and finish WebAssign. I would also recommend looking at the back of your unit outline. Those are also really good questions to look at before the test. Okay. So just a reminder, I wanted to show you the Java Lab website again that has the simulations. So if you go to the home and then on the top left, you can see I selected the electricity and magnetism tab. Second from the bottom on the drop down is the electromagnetism. Click on that and you'll get here. You guys have seen these before, so I won't talk too long about them. If you scroll down though, on the left there's our right hand rule for the straight wire. Thumb's the current because the wire's straight. Then in the middle right there, for me, it's the looping wire. All right, so again, it makes sense to use your fingers as the current because it goes around the looping wire. And the last one was an add-on to the situation we already knew, which was, again, a current carrying wire does create its own magnetic field, but then if it's also in a magnetic field coming from some external object like a bar magnet, you have two magnetic fields and now a force. All right, third right hand rule helped us determine this force, and I do want to show you real quick before I go to the final idea. I want to show you guys our equation for this. Was the magnetic force was dependent upon how much current was going through that wire, the length of the wire in the external magnetic field, and the external magnetic field itself. I won't write it with a subscript ext on your unit outline equations, it's just B, but that's maybe a nice reminder for you guys, okay? So that stuff we've already learned, just wanted to do a quick reminder where you could go to find some of that information. The new idea is not really new, it's just a different scenario. So if you think about the last rule that we did, it was always charges moving through a wire, which means they were trapped in a wire. So there's a different situation. Well, what if it's just moving charges? You could say positive particles or protons, but they're not trapped in a wire, they're just moving freely in space. It is technically a kind of new situation, but the big idea is still the same. So there is another website that I want you guys to navigate to. It's called ophysics.com, and this is the home for it. So like all websites, if you look at the tabs there, you can see E and M in the middle, and then if you look about a little past halfway down, there's a charged particle in a magnetic field. So I'm going to select that, and it won't show us a million situations, but it does a great job giving us a visual and relating it to what it's used for in the real world. So there's a lot of stuff on the left. It's basically saying you're going to have a particle of some mass, give it some velocity, it will have a charge, which is so important for this to occur, and it's going to move through finally an external magnetic field, which is that magnetic field strength. Now, you can't actually see where the particle starts, and I wish I could circle it, but I'm not a notability. The particle is actually right next to the magnetic field strength units. You see the T in parentheses for Tesla. Just to the left of that first parentheses is a dot. That's actually the particle for this simulation. So, what's going to happen with this simulation is it's going to have some velocity to the right, and it'll reach and enter that peach region, which is representing a space that has a magnetic field, an external magnetic field. So that wouldn't be the field created by a moving charge. So the good news is, if you think about it, if this is a proton, even though this particle's in space, it's the same idea as a proton moving through a wire. That's what conventional current is. So we're actually still going to have our thumb represent the quote-unquote current. It's the velocity of the particle, which will be to the right. Now, to make it easy right now for us with your right hand rule in class and help each other with this, you guys are good at doing that. Right now that pink region shows a field coming out of the page because it's dots. I'm actually going to start with one that's into the page, so I'm going to reverse the direction, and that's what the X's are now showing us. So let's do this together real quick. Even though it doesn't show the particle moving to the right, when I hit play or start, it will. So everybody point your right thumb, right hand, remember, your thumb to the right of the page, okay? Your fingers then for this rule are representing the direction of the external magnetic field. So keeping your hand flat, roll your wrist, all right, or elbow, kind of move around so that your thumb stays pointing to the right of the page, but your fingers are pointing into the page. All right, right now, pause it, take a moment to think, which way will this particle be forced if it is a positive particle moving to the right in a field that's into the page? Go ahead and pause. All right, if you said to the top of the page or up, you are correct, because your palm, when you hold your thumb to the right of the page and your fingers pointing into the page, your palm pushes protons. So if it's a positive particle, your palm is pushing them, and that would be to the top of the page. Now, this will be hard for me to show you guys with me not being there and trying to do this over this little video, but if you kind of hold your hand, so your thumb's to the right, fingers are into the page, and palm is to the top of the page, if you take your other hand, like your index finger, and just push your right thumb, what that would do is it would make the particle turn. So it would now kind of be going up and to the right. All right, because that's what forces do. They can make objects change their velocity, in this case, their direction. When you do that, though, what's interesting is when my thumb is now pointing up and to the right, my palm actually has a new direction. So since you have a new velocity, your kind of hand rotates, which makes the force no longer straight up, but up and to the left. What this will do is it'll continue turning, and it'll make the object go in the shape of a circle. All right, so you can actually hit show radius, which gives away the answer, but this idea with particles moving freely in space, there it goes to the right, this idea actually makes them turn. And if you guys YouTube particle accelerators, like the Large Hadron Collider, Fermilab, you will find out, okay, that's, I guess, how they get them to go in these gigantic rings that have multiple mile diameters. They use magnetic fields to make them turn, electric fields to make them speed up. So kind of advanced physics, but there's the application of that, okay? We could also try this if I reset it and kind of clear the old ones. You could vary some stuff and say, all right, what if now the field is not out of the page but into the page, or excuse me, vice versa, my bad. It's not into the page but now out of the page. Particle is still going to be positive, it's still going to be moving to the right, so try this with your right hand. All right, can you point your thumb to the right of the page with your fingers pointing out of the page? Kind of tough, but pause and give it a shot. All right, if you said to the bottom of the page, awesome. Okay, you basically had to kind of, I don't know how to describe it, just point your finger straight at you. So now your palm is pointing to the bottom of the page. I can check that with this simulation, hit start, and awesome, it actually went the other way. The other thing that could happen is, well, what if it's not a proton? What if it's an electron? All right. I don't want to do anything different, even though you can, depending upon who is teaching you or who you collaborate with. I still want to use my right hand. But now if the particle is negative, okay, we're going to have to do something at the end. So let's go back to a situation where field's into the page, particle has a velocity to the right. So everybody, again, thumb to the right, fingers into the page. My palm is pushing protons up, right? Well, it's an electron, so don't overcomplicate it. If it's an electron, it's just not up. It's to the bottom of the page, it's opposite. Okay, so it's kind of your knuckles. Your knuckles are telling you which way a negative charge will be pushed, and there we go, it's confirmed by that. All right, so that's the conceptual stuff. You have to practice this, of course, with your hand. You'll get some of that on WebAssign, and even if you guessed before, do it again. All right, now that you know the right hand, because you know it could show up on the test. All right, let's do a little bit of the math, though, so let me switch over to Notability, and let me show you how it relates to the current carrying wire, because like I said, this really isn't a new idea. What's kind of interesting is if you think about what current is, if you remember from circuits, current is the charge that flows over some amount of time. So if I replace current with that equation, Q over T, but then still have it times length and then times the external magnetic field, what's interesting is length divided by time, which is also kind of like distance divided by time, that's velocity. So the equation for a particle moving freely in space and not confined to a wire, it might look like it's a new equation, QVB, but it's not. It's actually the exact same equation, it's just represented with variables that are more appropriate for an individual particle moving with some velocity in space. Okay? So this is how you would solve it for a particle moving freely in space. This is for if it's a conventional current carrying wires. Something else, if you're curious, I don't think there's anything on WebAssign with this or even your unit outline mathematically, but if it does pop up, I want you to be aware. If you think about in the simulation I showed you, the particle was changing its direction. So that is an acceleration. So you might kind of give me these wide eyes right now, and I know I laugh along with you, but what's kind of interesting is we would still actually apply Newton's second law because it's changing its direction, so it is accelerating. This is a centripetal acceleration, though, which is being caused by the magnetic force acting on this particle. And you could, if you wanted to, recall that centripetal acceleration is equal to v squared over r. So I know right now you're probably like, oh geez, like this again? Yeah, it's a big idea though, and it's not that bad. But that's another way objects can accelerate. It could be from a different type of force, in this case, a magnetic force, okay? All right, guys, hope this was brief enough. Hope it helped you out a little bit. And again, collaborate with each other. You guys know that a lot of the questions will be on using your right-hand rule. All right, it'll be very conceptual with that. So feel good about those 3 situations. And I will see you guys on Tuesday, okay? Good luck, everybody.